Section 7.2 begins on page 486, and this section is on exponential decay functions. The important thing to understand is that there is very little difference between exponential growth and exponential decay in terms of how they operate. They look different, but they don't work any differently. Remember, in the previous lesson, we talked about an exponential growth function, or an exponential function in general, that has this kind of form. And to be growth, b had to be greater than 1. So this was growth. What we're going to deal with now is the exact same type of function, but now we're going to deal with what happens when b is between 0 and 1. And it turns out that when b is between 0 and 1, these become decay functions. And whereas a growth function would start near its asymptote, so let's say the x-axis was the horizontal asymptote, it would start near its asymptote and it would grow away from its asymptote, either in the positive direction or in the negative direction in case a was a negative number. So this was growth. Could look like one or the other. Now for decay, what's going to happen, let's say we have the same horizontal asymptote. Now for decay, what's going to happen is they're going to start farther away from their asymptote, and they're going to grow closer and closer to the asymptote as we move from left to right. And so this is the type of look that we're going to get, one or the other. This would be for positive values for a, this would be for negative values of a. So for example, what we may be dealing with now is f of x is equal to, instead of 2 to the x power, maybe we have 1/2 to the x power. And so when you go to graph this, again, I suggest making a t-chart. Choose your center value that will make the exponent 0. In this case, that's just 0. Plug in 2 numbers larger, 2 numbers smaller. This will keep your numbers generally relatively easy to work with in most cases. 1/2 squared is 1/2 times 1/2, which is 1/4, which is 0.25. 1/2 to the first power is 1/2, which is 0.5. 1/2 to the 0 is 1. 1/2 to the negative first power becomes 1 to the negative 1 over 2 to the negative 1. So this wants to move up, this wants to move down, and you end up with 2 over 1, or just plain old 2. If I make this the negative second power, these both become negative 2's. This becomes 2 squared over 1 squared, which is 4. And so when we go to draw the graph of this, get this out of the way a little bit. So when we go to draw the graph of this, we see something very similar to the previous example. Notice that there's nothing being added or subtracted out here after our exponential term, so that means that our horizontal asymptote, it's going to follow the same rule as the previous section, is going to be y is equal to 0. So here's our y equals 0. There's our horizontal asymptote. Make sure you draw it in to help guide your graph. And we have negative 2, 4, negative 1, 2, 0, 1. We have 1, 1/2, and 2, 1/4. And notice that this thing is going to grow towards its asymptote rather than away from it as we go from left to right. Don't let it actually touch. I don't care if the arrowhead touches, but don't let the curved part actually touch. And there's our graph. So whereas the other one, 2 to the x power, went this way, this one goes in this direction. Now as far as domain and range, it's going to work exactly the same way. Your domain is always going to be all real numbers on these exponential functions, because if I shade this towards the x-axis, this thing is going to continue this way forever, and it's going to continue getting closer and closer, but it keeps going that way. It will cover the entire x-axis. If we connect it to the y-axis, however, it's only going to connect above its asymptote in this case, and so this particular one is going to give us y greater than 0. If it was one that was coming up like this, then it would be y less than 0. So in terms of what you're going to be doing in terms of graphing them and things like that, this works exactly the same way as the last section. So again, the only difference is going to be the basic details of which way the graph is curving, but it's going to have the same overall look. So the other thing they're going to ask you to do from time to time is they're going to ask you to take a look at an equation like this. And they're going to ask you, is this growth or decay? So what you need to do is notice that your power here is x minus 2. That's our expression in terms of x. Pay attention and make sure there's no negative on the x, because that's actually going to change our answer and make it the opposite of what it seems like. I don't believe they actually give you any of those in the book. But if they do, that will reverse your answer. This one doesn't have a negative on the x. The negative is on the 2. All we need to look at is we need to look at the number being raised to the power, the base. Since 1.3 is greater than 1, this is a growth function. Whereas if we had this, now our base is 0.25, and since 0.25 is less than 1, this would be a decay function. The idea is that 1 is the breaking point. If we're raising 1 to a power, no matter what the power is, no matter what we plug in for x, this section is always going to give us 1 times 0.25. We're going to get 0.25 for every single value of x. That's going to keep us exactly the same. We're not going to grow. We're not going to shrink. No growth, no decay. If this number being raised to the power is larger than 1, then as we raise it to bigger and bigger powers, we get larger and larger answers. And so as x gets bigger and bigger, we get bigger and bigger answers, either in the positive direction or if there's a negative out here, in the negative direction. But this is getting larger, this distance from the asymptote. Whereas if this number is less than 1, we're multiplying by something less than 1, which is going to shrink us as we go from left to right. And that's when we're going to start to get something like this, where this distance is getting smaller and smaller. So that's the idea between growth and decay. Now, don't forget that just like with growth or any exponential function, if you have something like 2/3 raised to the (5x minus 1), you're going to want to choose as your center value whatever makes this 0. So in this case, this is kind of an ugly one. But if you make 5x minus 1 equal to 0, you get 5x equals 1, x equals 1/5. So what I would do on a t-chart there is I would plug in 1/5 as my center value. Getting larger, I would do 1 and 2. Getting smaller, I would do 0 and -1. I would use whole numbers for everything else. You don't need to use fractions just because the center number is a fraction. But making that 0 and then picking numbers on either side will make it easier to graph. And also, just like all exponential functions, if you have something like y equals 2/3 to the x plus 2 minus 4, when you go to look at the horizontal asymptote, all you really look at is the stuff that comes or is not directly attached to the exponential term. So if there was even a 3 out here, this stuff is the exponential term. This would give you a horizontal asymptote of y equals 0. The only thing that's going to change that is if there's something added or subtracted out here, and whatever's being added or subtracted, y is then going to equal that number as your asymptote. So this would have a horizontal asymptote of y equals -4. You want to draw that on your graph to help guide your graph so that you don't bump into it or cross it by mistake. That's our lesson.